Gradient descent is a great algorithm for optimization, but one of its shortcomings is that it can be slow when the function is ill-conditioned. The curvature behaves very differently in different directions, and the gradient does not point towards the minimum of the function. One approach to this problem is to use second-order information to correct the direction. An increasingly popular method is the natural gradient of Amari. It adapts to the geometry of the problem using the Fisher information matrix. But many implementations of natural gradient methods in machine learning do not compute the Fisher. Instead, they often use the outproduct of gradients, which has been called the empirical Fisher. The two matrices look similar, but some authors have warned against this approximation. Our work looks at the relationship between those two matrices in more detail. We show that even on very simple problems, using the empirical Fisher can lead to very bad results. The main difference between those two expressions is that the Fisher uses the probability distribution of the model to sample outputs, but the empirical Fisher uses samples from the training data. It loses the connection to a Fisher information unless the two distributions are equal. This is not possible when the parameters have not been fit to the data, as is the case during optimization. On ill-conditioned problems, where gradient descent struggles but natural gradient converges quickly, preconditioning with the empirical Fisher does not guarantee the same improvement. Looking at the angle between the empirical Fisher direction and the natural gradient reveals that the two can even be opposite. The situation improves at the minimum, but even there, the empirical Fisher needs specific conditions to equal the Fisher. The models need to be correctly specified, which is the case on this classification and regression problem. But this is often understood just as being a good model. Correct specification is more subtle, and small deviations that are difficult to know in practice lead to very different outcomes. Our paper provides an overview of the known connection between the Fisher information and other quantities used in second-order optimization, such as the Hessian and the generalized Gauss-Newton matrix. And we provide a detailed criticism of existing arguments showing connections between those quantities and the empirical Fisher.